Okay. In this video, I want to talk about how to multiply two vectors together. So let's get to it. Okay, so we've talked about addition and subtraction already, and also multiplication by a scalar, but we haven't talked about multiplying two vectors yet. Because the addition was component-wise addition, I think maybe the first type of multiplication I can think of is what I'm going to call naive product. That's not an official name, but I call it that because it's probably the first thing that I would think of. So that might be a component-wise multiplication. So if the components of one of the vector is a1, a2, a3, and the other one is b1, b2, b3, just kind of multiply component-wise and create a new vector like this. It turns out that it does have some uses, but it's actually not as useful as it might first seem. And really the reason that this doesn't really give us anything that important is because that this does not, whatever you get actually kind of depends on which coordinate system that you pick, right? The X, Y, and Z coordinate that you put up, depending on how you orient it and where you place it, you'll get a different vector in the end. So you want your operations to have some kind of geometrical meaning that's kind of independent of the coordinate system that's kind of lying in the background. So let me suggest a different type of a product, and this one is called dot product. In fact, it's important enough that it has a lot of different names. So sometimes it's called dot product, sometimes it's called inner product. How is that computed? So it's not too far away from component-wise multiplication. What you do is you multiply the components together and then add it afterwards. So what you get when you compute a dot product is not another vector. You just get just a number. It's a scalar in the end. So this is what dot product is. So let's just kind of compute a few of these. So you could kind of multiply two vectors like this. You just multiply the components. So 4 times 6 is 24. 1 times -3 is -3. And 1/4 times -8 is -2. If you add them all up, you get 19. Here's a similar type of computation using the IJK basis. Here, the first vector does not have a j component. So you just assume that to be 0. So 4 times 2 is 8. 0 times 1 is 0. And 9 times -1 is -9. So you could get a negative dot product as well. One thing to note is that this gives you a kind of a way to write the length in terms of the dot product. So if I take vector and dot product by itself, then that means we're going to be squaring each of the components and then adding it together, which is pretty much the formula for the length or the magnitude, except there's no square root. So this thing is the same thing as the length squared. So if you take a dot a, that you get magnitude of a squared. Okay. So you might be thinking, you said the naive product sucked because it didn't have a geometrical interpretation, but it looks like I'm using a component, so it looks like it depends on the 3D axis that you've set up. Well, it turns out that it's independent of how you place the axis, and let me prove it to you. Okay, so this will use what's called law of cosine from pre-calculus class. I hope you remember. So it's okay if you don't remember, I'll remind you. It's usually written something like this. If you have three sides of a triangle ABC, and if I draw an angle between the sides A and B so that it's on the opposite side of the third side C, then the law of cosine says C squared is equal to A squared plus B squared minus 2AB cosine the angle between A and B. It's kind of like a generalized formula for, it's kind of like Pythagorean theorem. If I remove this and change this to 90 degrees on the angle here, we get Pythagorean theorem. The cool thing about law of cosine is that you can use it for any triangle, not just a right triangle. Okay. So if you kind of use this law of cosine in the setting of vectors, so kind of imagine there's vector A and B here, and this is the vector B minus A. So if you take negative A plus B, then you'll get B minus A here. And then kind of apply the law of cosine here. So this is the side C. So take the magnitude of that guy squared. That should be equal to the magnitude of A squared plus magnitude of B squared minus 2 times magnitude of A times B times the cosine of angle between them. And remember that the magnitude squared is same thing as A dot, the vector dotted with itself. So you can look at the left-hand side. So B minus A dotted with B minus A. And I haven't proved this yet, but you could, dot product satisfies the distribution law that of the regular multiplication. So this is the same thing as B dot B minus B dot A minus A dot B. Minus A times minus A is going to be plus A dot A. So this is the left-hand side. And maybe you can see from the formula that because we do component-wise multiplication, and regular multiplication doesn't, it's commutative. It doesn't matter which way you multiply. B dot A is same thing as A dot B. So in that case, we can just kind of combine these two. So we get magnitude of B squared minus 2 times A dot B, because these two, the two middle terms are the same thing, plus magnitude of A squared. So this is the left-hand side, and this is supposed to equal the right-hand side of the equation. Okay. Notice how the magnitude squared on both sides of the equation will cancel out. And left-hand side and right-hand side has -2 in front. So maybe divide both sides by -2. And we get this new formula for the dot product. Okay. Here we go. So the dot product could also be computed by multiplying the length of the two vectors, or the magnitude of the two vectors A and B, and multiplying by the cosine of the angle between them. Now notice how this formula does not depend on the components of A and B at all. The length of the arrow doesn't depend on the coordinate system. And angle between two vectors, two arrows, does not depend on the coordinate system either. So we have a different formula that kind of doesn't depend on components. Now, don't get me wrong. If you have a vector in a component form, it's easier to compute the dot product this way. But we have another way to compute it if the information you have are about angles between vectors and magnitude of those vectors. And we get a bonus. If we know how to compute these things in two different ways, we could use that to come up with a new formula. So look at this dot product and solve for the angle theta instead. Okay, so divide both sides by the magnitudes and take the inverse cosine of both sides. So then the angle between two vectors is ArcCosine of the dot product divided by the magnitude of each of the vectors. Now, this is very useful because now this gives us a way to compute between any two vectors. And that's a difficult thing to do, especially in 3 dimensions. So if it's a 2-dimensional picture, you could just kind of hold a protractor. You can kind of break out your protractor from your maybe middle school pencil bag and kind of measure this angle using that. But if it's a 3-dimensional vector, what are you going to do? Like 3D printies and then hold it up next to a protractor? No, right? So this is nice to be able to compute angles between two vectors in 3 dimensions. Okay, so here's how to use them. So for example, we have 3 points, P, Q, and R. And imagine this in 3-dimensional space. And we want to compute, let's say, the 3 angles in this triangle. How do you do it? So we don't have to 3D print them, right? What you could do is you can kind of form vectors out of these. So maybe I'll compute the angle at P, right? So we could get 2 vectors, PR and PQ. So remember, when I want to draw a vector between 2 points, I subtract the components of the head of the arrow minus the tail of the arrow. So if I want to draw a vector from P to R, I take the components of R and subtract the components of P. So 2 minus 1, 2 minus -3, and -3 minus -2 is -1. And vector from P to Q is going to be 2 minus 1, 0 minus -3, and -4 minus -2. So that's -2. Okay. I need to also compute the magnitude of these things. Okay. And now I have all the ingredients to compute the angle at P. So we could just kind of plug it in. So if we take these 2 vectors and look at the dot product, so ArcCosine, the dot product is 1 plus 3 times 5 is 15, plus -1 times -2 is +2, divided by root 27 times root 14. And you're gonna need a calculator for this. So I'm gonna compute it in radians. So let's see, let's compute the inside first. So that's 18 divided by square root of 27 times square root of 14, paying attention to where the parentheses go. This is the same thing as ArcCosine of 0.9258. Okay. And inverse cosine of that is 0.38759 radians. Okay, so that's really cool. I was able to compute the angle there. So one thing to note that's good to know is that if when you compute the inside, if the numerator kind of determines the sign of this expression. So if the dot product is positive, what you'll get is an acute angle. So acute angle is the angle less than pi over 2 radians or 90 degrees. If it's exactly 0, the dot product is 0 means it's exactly 90 degrees or pi over 2 radians. And if it's negative, then it's going to be obtuse angle. So that's a wide angle that's more than 90 degrees or more than pi over 2 radians. So the dot product kind of detects if the angles are kind of pointing with each other or away from each other or exactly 90 degrees. Okay. All right. Let's do one more application. So this is like a structure of like a methane molecule. So methane compound is one carbon with 4 hydrogen attached to it. So you might write CH4, or you might write the structure in this way, but really this is like the chemical kind of squished into 2 dimensions. These chemicals live in 3 dimensions. So what it really looks like is it's kind of like this. It's in the shape what's called tetrahedron or regular tetrahedron. So the carbon element is at the middle of this triangular pyramid, and there's like 4 regular triangles that's kind of forming this pyramid. And these vertices are the locations of the 4 hydrogen molecules. And what you might wonder is like, what is that angle that's made by 2 hydrogen bonds on a methane molecule? We can 3D print it and measure it with a protractor, or we could do some geometry using vector. So to compute this angle, I'm going to use a trick. So the trick is to use this. Instead of kind of drawing a regular tetrahedron, what I'm going to do is I'm going to draw a unit cube. Okay, that's kind of sitting at the origin at one of the corners. And cube has 8 different kind of vertices. And I don't know if like this will kind of test the limits of your imagination, like visual thinking. If you can kind of imagine coloring every other vertex blue. I did not do that correctly. Okay. So every other one blue and every other one green. Okay, just ignore the green ones. Just look at the blue ones. If you connect all the blue vertices, you will get a regular tetrahedron that's kind of sitting inside of that cube. So we colored every other one. So each of these edges between the two vertices is kind of cutting across a square. So they all have the same length of square root of 2. And then the carbon is sitting at the center. So this is a unit cube. So the center of the tetrahedron is the center of the unit cube. So that has the coordinate 1/2, 1/2, 1/2. And there's 4 different hydrogen. They all kind of make the same angle. So I'm just gonna pick 2 of these coordinates. So let's say hydrogen 1 is on the x-axis. And here's the hydrogen number 2 is on the y-axis. Okay. All right. So what I want to measure is this angle between carbon to hydrogen 1 and carbon to hydrogen 2. So subtracting the head of the arrow minus the tail of the arrow. That's the vector from the carbon pointing to the first hydrogen. And similarly, this is the vector that's pointing from the carbon to the second hydrogen on the y-axis. We can compute the magnitude so it's 1/2 squared plus 1/2 squared plus 1/2 squared. And magnitude of the other vector is exactly the same. So now we have all the components. So let's compute it. So the angle between the 2 hydrogen bonds is going to be ArcCosine of the dot product of these 2 vectors. So let's see, 1/2 times negative 1/2 is negative 1/4 minus 1/4 plus, because the third coordinate has both negative 1/4, all divided by the 2 magnitudes. So root 3/4 times root 3/4. Let's see. So we have negative 1/4 divided by root 3/4 times root 3/4 is just going to be 3/4, or ArcCosine of negative 1/3. And this time I'm going to compute it in degrees because I think a lot of chemists prefer degrees over radians. And it's a negative 1/3, so it's going to be obtuse angle, right? It's going to be larger than 90 degrees. And in fact, it's 109.471 so on degrees. So if you have taken a chemistry class, you might have memorized this number, 109.47 degrees, and that's the angle of the hydrogen bonds on our methane. Right? I thought that was a pretty cool thing to calculate. So I think I'll end the video here. See you later.